All right, guys, Professor Hildebrandt here. This is going to be the Chapter 4 kind of overview lecture going through the PowerPoint slides. And then later on, I will also make sure that I have some additional examples. There is some math involved, some calculations, of course, in this chapter also. And so I will provide some additional examples for you guys to look at. Again, we're just working through, it's kind of a continuation of what we were doing in the last chapter. So we're still trying to describe our data. This time we're looking a little bit more at different ways that we can display the data. I will say we're skipping the first two learning objectives in this chapter on dot plots and stem and leaf. So if you're reading through the text, you can just go ahead and move right past those. So we're going to jump straight to measures of position, learning objective 4.3. And this one is talking about locations in terms of percentiles. So we talked about in chapter 3 that the standard deviation is the most widely used measure of dispersion, but another method of describing dispersion is with measures of location. And so this is the formula that we could use to find any percentile where P, so our P up here in our formula, represents the percentile we're trying to find. And then as it was in the last chapter, your N is the number of values in our data set. So if we were looking for quartiles, then we're going to divide into 4 equal parts. And so for the first quartile of Q1, our P would be 25, right? And then for quartile number 2, the P would be 50. And for quartile 3, the P would equal 75. And then whatever, again, our N is just however many observations or values are in our data set. And so notice too that this formula for location of a percentile, it helps us find our median, right? So our quartile 2, using the 50th percentile, is going to help us find our median. Just like we mentioned in chapter 3, if we're trying to find the median value in a data set, we first have to put our numbers in order. So we need to rank them from smallest to largest. Quartiles are very often used to describe measures of location, but we also use deciles where we're dividing into 10 equal parts. And then also we use percentiles where we're dividing them into 100 equal parts. And so I know we've already talked a little bit about percentiles going all the way back to chapter 1. You're asked to do some calculations. But so those are the 3 most common. So like for a percentile, if you're told your GPA is in the 94th percentile, then that means 94% of the students have GPAs lower than yours. Okay, so that's kind of the meaning behind it. So again, the median is the second quartile, or sometimes we call it the middle quartile. And then over here we have the first or lower, and then on this end, the third or the upper. And then this middle part here, so the difference between quartiles number 1 and the third one, we call it the interquartile range. Okay, so that's just some terminology. But let's, and it covers, so that interquartile range is going to cover 50% of the data. But let's work through an example. So Morgan Stanley is this investment company. They've got offices all over the country. And here are the commissions earned last month by just a sampling of 15 brokers, right? So the population would be all of the brokers. Obviously, Morgan Stanley is a large company. There's many more than 15. We're just looking at 15. So we have all of these numbers here. And again, the first thing we're going to do is sort our data from smallest to largest. And so we've done that here for you. Now we're going to work on finding the median, the value in the middle. Again, we have 15, so our N is 15 brokers in my sample here. I'm trying to find the median, so that's the 50th percentile. So it's 15 plus 1 times 50 divided by 100, or 8. Now, 8's not the answer. The value, the median, is not equal to 8. What we say is the median is the value at position 8, okay? And so again, down here, I have all of them listed again. So if we count over, 1, 2, 3, 4, 5, 6, 7, 8. So we would say that the median for this data set is $2,038. Now we can also find our first quartile, where we're in the 25th percentile, and then also our third quartile, where we're in the 75th percentile. So we use the same method. For the first, it's the value at position 4. Well, this is position 4. And so the answer there would be $1,721. And then position 12 for the third. And this is position number 12. Okay. Now, this one is fairly easy because I gave you to start off with an example where you simply count positions. And so it's not too bad. Doesn't always work that way though. So let's look at one where it doesn't work that way. So in this example, I'm going to show you that sometimes the values that are our quartiles are not part of the data set. So just like when we talked about median, and I said if we had an even number, then the median is the average between the two in the middle. So it's not a number in our original data set. It's going to kind of work the same way. So I've already put our data in order here from smallest to largest. Okay, my N is 6. There's 6 values here in my sample. And again, my formula is the location of the percentile I'm looking for. Let's just do quartile 1, so the 25th equals N plus 1 times P over 100. Okay, and so when we're plugging this in, we have 6 plus 1. The percentile we're looking for, the 25th, over 100. And so when you do this math out, you would get 1.75. So not an even number. So again, what does 1.75 mean? It means that the first quartile is the value at position 1.75. Well, where the heck is the position 1.75? Well, this is position 1. And this is position 2. So 1.75 is in between these two. So it's 0.75 of the distance. So 0.75 of the distance between the first and second positions of our data set. Okay, so we're going to do a little bit of math here to figure this out. First, we need to know the difference between 1 and 2. And so we're going to find that by just taking 61 minus 43, and we get a value of 18. Okay, then we're going to take that 18 and multiply it by 0.75 to get a value of 13.5. Almost there. So the value at position 1.75, so position 1.75 is the starting position 1, 43, plus 13.5, which is 56.5. So that is my first quartile. Okay? And again, I'm going to work, I'll make sure I have another video that works another example like this. All right, so let's move on to box plots. I'm just going to spend a second on this one. Box plots is just really a graphical way to display our quartiles. So there's a minimum, there's a maximum, there's the median in the middle. We have a first quartile on the lower end, and we have a third quartile on the upper end. Okay, and again, that interquartile range is Q3 to Q1. So Alexander's Pizza offers free delivery within 15 miles. How long does the typical delivery take? And within what range are most deliveries completed? So he looks at a sampling of 20 deliveries, and he figured out the minimum time was 13 minutes. The max was 30. The first quartile was 15. The third quartile was 22. And the median was 18. And so we're going to draw out this box plot here. And I'm not really going to get into all this because I'm not asking you guys to draw this. I just want you to be able to look at a box plot and kind of understand what it's saying. And so the biggest thing I want you to take away from this graphical representation here is that we would say that this data, we say it's positively skewed, because that's where we're going next in the chapter, is to talk about skewedness. So it's positively skewed. How do I know that? Well, there's two indicators here. First, let's look at our median. Our median is not in the middle, right? It's not in the middle of my box, my green box. There is more space over here on the right, on the positive side, okay? There's also more space here between my third quartile and my max than there is down here between my first quartile and my minimum. So again, for the purposes of this class, I want you just to be able to look at a box plot and tell me, looking at this one, yes, the data is positively skewed. So then as another example, let's look at this one just really quickly. Again, my median here is not in the middle, right? The middle of the box would be more right here. That's not where it is. This time there's less space on this side, on the positive side. And so we would say that this data set is negatively skewed. So that's how we tell skewedness when we're looking at box plots. But let's look at some graphs to also show that, and then we'll move on to actually calculating the skewedness of a data set. So we might have, and these are kind of the most common shapes of data. So our first is symmetric, and you can see that nice perfect bell curve, right? And when we have symmetrical data, it means that our mean and our median are the same. So they're equal to one another. The second graph here, so graph number 2, is showing a data set that's positively skewed. And when it's positively skewed, or we say skewed to the right, then your mean is greater than the median. So you can see here the mean is higher than. For number 3, negatively skewed, it'll be the opposite. So we call this left skewed. And this time our mean is less than the median. We could also have something kind of crazy like over here in number 4 called bimodal. And a bimodal shape is when we have 2 or more peaks. And usually it indicates that we've taken 2 or more populations and combined them together into one graph to compare them to one another. Okay. So, last topic for this chapter then, learning objective 4.5, skewness. So this was developed by Professor Carl Pearson, and he just developed a simple formula for calculating the skewness of data. And he was specifically looking at differences between the sample mean and the median, and then dividing that by the sample standard deviation. And so this is the first formula that we'll use, and it's called Pearson's coefficient of skewness. So we say SK equals 3 times, again, the difference between the sample mean, remember that's X bar from the last chapter, minus the median, divided by S, where S is our standard deviation. When we calculate this, you'll get a coefficient anywhere from -3 to a +3. So to just give you some examples, if you had a value of 0, then our distribution is perfectly symmetrical. That's where the mean equals the median. That's why we would get a coefficient of 0. If we had something like 1.63, we'll say, okay, that's moderately positive skewedness. Whereas if we were close to -3, we would say considerable negative skewedness, okay? So let's work out an example. Here we have some earnings per share for a sample of 15 software companies back in 2016, and we've already arranged those earnings per share from smallest to largest. Some of the work has been done for you. So in order to calculate our skewness coefficient, first we have to find the mean, right, our X bar. We have to find the median, and we have to calculate the standard deviation, S. We're going to need all of those things in order to use the formula 4.2 that we were given. And so we're going to do that, and then we're going to make some observations about the shape of the distribution. So here we go. So first, we're going to calculate the mean. Again, the X bar, and some of the stuff, hang on y'all, some of it didn't transfer over, but let me just So x bar equals the sum of all the x's divided by n. Again, we had 15 observations in our sample, and if we summed up all the values, it would be 74.26. So my mean here is 4.95. Okay, then we're going to calculate, again, I don't know why the formulas didn't carry over, but here we go. Let me fix that. There. So now we're going to calculate the standard deviation. You can see they're just kind of putting it all in one, right? And when we talked about standard deviation in chapter 3, I said, don't do it that way. You're going to mess something up. So let me get us a clear thing here. All right, so if we recall, our s squared, or variance, is the sum of all of my x's minus my sample mean x bar squared divided by n minus 1, and then my standard deviation then, s, was the square root of all of that. Okay, so again, and I'm not going to work this out, but what I would do here is I would start out with some columns, and I would have my x's. So if we go back over here, 0.9, 0.3, right? So 0.09, 0.13, all the way down through 15. And then in my second column, I would do the difference between the x and the sample mean. And so remember, that was 4.95. So you would just subtract the 495, okay, and get those values. And then in my last column, I'm taking that difference and squaring it. And once I have all of those, I sum them up, right? And then divide by n minus 1, okay? Again, I'm not going to do that right now, but you guys need to practice that. So I would suggest y'all do that and see if your answer then matches my example here, where I'm saying that my standard deviation is 5.22. So now that I know my standard deviation, I can compute my skewness. So it equals 3 times x bar minus the median divided by s. So again, our median was 4.95. We find our median value by looking in the middle. It's 318. We divide by this standard deviation that we just calculated of $5.22. And so we get a coefficient of skewness of 1.017. So what would we conclude? We would conclude that this data is moderately positively skewed, right? It's not extremely positive because it's not too close to 3, but it is definitely positively skewed data. So there's a second formula here called the software coefficient of skewedness, okay? And this is the one I'll try to find or make a video for, an additional one. So, because I'm not going to work it right now, but the formula is, and it's in your textbook, so I wanted to go over it quickly, n divided by n minus 1 times n minus 2, and then all of this times the summation of the differences between our x values and our sample mean divided by the standard deviation, all of that cubed, and then again, then we sum up all the cubes and multiply times this n over n minus 1, n minus 2 stuff. So again, you could take the example that we just did and use those numbers. You already know your x minus x bar, right? That's your column 2 that you were working on. So then you would just divide that, sorry y'all, my iPad's not liking me this morning, by that standard deviation, and then cube it. Once you have all of those cubes, you would sum them up and then again multiply times this. So that's the second method. All right, last thing here, scatter diagram, just a graphical tool to portray this relationship between our variables. If our scatter points move from the lower left to the upper right, then we say there's a direct relationship here, or positively related. And if it's the opposite, upper left to lower right, we say negatively related or inversely. So example 1 here is a positive relationship. Example 2, you can see, is more negative. And then the last one is just, kind of all over the place. So we would just say that there is little relationship between, what's our data here? The height of a supervisor versus their annual salary. Okay, so that's chapter 4. More to come soon.